Welcome back. Over the last few lessons, we tamed the voltage decay bias. One divider sets the base, and the operating point barely cares about beta. Today, we keep that idea and raise the stakes. Two transistors, stacked one on top of the other, sharing a single bias divider. And look at that divider on the left. Not two resistors now, but three. That longer ladder hands us two different base voltages at once, one for each transistor. Our job is to find four numbers, the collector current and the collector-emitter voltage of each transistor. Here is the picture to hold in your head. Imagine one pipe running top to bottom with two water turbines stacked inside it, one above the other. The same stream turns both. Whatever flows through the top turbine must flow through the bottom one too. That single shared flow is the key to the whole problem. It looks like twice the circuit, but it is not twice the work. Let us see why. Before any numbers, let us read the circuit and make three observations that turn it from scary into simple. First, one divider, two taps. The supply pushes a single current down through all three resistors in series, and we read off a voltage at each junction along the way. The lower junction feeds the base of the bottom transistor. The upper junction feeds the base of the top one. Second, one current path. Follow the heavy line. Out of the supply, through the collector resistor, down through the top transistor, straight into the bottom transistor, and out through the emitter resistor to ground. There is only one road, so the same current flows through both transistors. The top collector current equals the bottom collector current. We will lean on that hard. Third, the comfortable part. The divider is stiff, just like last time, so we ignore the tiny base currents and beta never enters. Now the trap. It is tempting to think two transistors means two separate problems, each needing its own beta. It does not. They are chained together by that one shared current. So here is the plan. Work from the bottom up. The bottom transistor's base and emitter resistor hand us the current directly, and once we have the current, everything else falls out. Step 1. The two base voltages, straight from the divider. Because we are treating the base currents as zero, nothing branches off into the transistors, so the divider is unloaded. One clean current down the ladder. That current is the supply over the total resistance. Add the three resistors, 7.5K plus 6.2K plus 3.9K is 17.6K. 20 volts over 17.6K is about 1.14 milliamps. Now the lower base. It sits above only the bottom resistor, so its voltage is that current times 3.9K. 1.14 milliamps times 3.9K and kilo-ohms times milliamps gives volts, is 4.43 volts. That is VB1. The upper base sits above the bottom two resistors together. 6.2K plus 3.9K is 10.1K. The same current times 10.1K is 11.48 volts. That is VB2. One ladder, two taps. 4.43 volts down low, 11.48 volts up high. No Thevenin, no loops, just the plain divider rule you have known since the very first resistor lesson. Step 2. The current. And here both transistors get solved at once. Start at the bottom transistor. Its base is at 4.43 volts. Cross the base emitter junction, drop the usual 0.7, and the emitter sits at 4.43 minus 0.7, which is 3.73 volts. That whole voltage sits across the bottom emitter resistor, 1K. Ohm's law hands us the current directly. 3.73 volts over 1K is 3.73 milliamps. That is the emitter current, and as always, the collector current is essentially the same. So the bottom transistor carries 3.73 milliamps. Now remember the single pipe. the same stream flows through the top transistor, so its collector current is the same 3.73 milliamps. Two transistors, one current found in a single step. And look back, where was beta? Nowhere. We never touched it. The base voltages came from three resistors. The current came from a voltage and one resistor. Swap in any transistors you like, beta 50 or beta 300, and this circuit lands on the very same point. And 3.73 milliamps is a healthy collector range current, exactly what we expect. Step 3. The collector-emitter voltage of the bottom transistor. Walk the middle loop, the one marked 1. Start at the upper base, 11.48 volts. Step down through the top transistor's base emitter junction, another 0.7 drop, and you land on the node between the two transistors. That shared node is the top transistor's emitter and the bottom transistor's collector at the same time. So it sits at 11.48 minus 0.7, which is 10.78 volts. From there, the bottom transistor's collector-emitter voltage carries us down to its emitter, and the emitter sits at the current times the bottom resistor. 3.73 milliamps times 1K is 3.73 volts. So write the whole loop in one line. 11.48 minus 0.7 minus 3.73 is 7.05 volts. VCE1 is 7.05 volts. The bottom transistor drops about 7 volts across itself, comfortably in its active region. Step 4. The last unknown, the collector-emitter voltage of the top transistor. Now walk the big outer loop, marked 2, all the way from the supply down to ground. Start at 20 volts. First drop. Across the top collector resistor, 1.5K carrying our 3.73 milliamps, which is 5.6 volts. Next comes the top transistor itself. That drop is the VCE2 we are after. Then the bottom transistor, which we just found, drops 7.05 volts. And finally the emitter resistor, 1K carrying 3.73 milliamps, another 3.73 volts. Those 4 drops must add back up to the 20-volt supply. So VCE2 is 20 minus 5.6 minus 7.05 minus 3.73, which is 3.62 volts. Quick check. 5.6 plus 3.62 plus 7.05 plus 3.73 is 20 volts exactly. Nothing leaked. All 4 unknowns are solved. Let us pocket the whole thing. 2 transistors stacked on one divider looked twice as hard and turned out to be one clean pass. The 3-resistor ladder gave 2 base voltages, 4.43 and 11.48 volts. The bottom transistor's base and emitter resistor gave the current, 3.73 milliamps, and because there is a single current path, the top transistor carries exactly the same. Then 2 loops finished the job. The middle loop gave 7.05 volts across the bottom transistor. The outer loop gave 3.62 volts across the top. 3 ideas carry forward. One divider can bias a whole stack. Stacked transistors share one current, so you solve them together from the bottom up. And once again, in a stiff divider, beta never shows up, which is exactly why real designs build this way. We have now solved these circuits with equations. Next time we do something different. We solve a transistor graphically by drawing a single straight line, the load line, across its characteristic curves and reading the operating point right off the page. See you there.